All right, so we have our object that's falling, and it's going to start with 0 velocity, and as time goes on it's going to speed up. So as it's speeding up, here it is. I'm going to draw its free body diagram. We have mg pointing downward, as always, and upward we have the drag force, which this problem says is equal to bv squared. So there's my free body diagram. And I like to write the equation that goes with that, so I could say d minus mg is equal to, and we're talking about the part of the motion where it's going to be speeding up. So it's going to be speeding up going downward, so that's a negative ma on this side. And instead of d, I'm going to go ahead and write bv squared. So bv squared is minus mg equals minus ma. And that's going to be my basic equation for this problem. Now in part B, they ask you what's going to happen to the acceleration over time. So we start out with a velocity of 0, and as time goes on, it's going to go faster and faster, so the velocity is going to increase in the negative direction. So let's look at what happens to the acceleration. If I solve this equation for A, I could say it's ma equals mg minus bv squared, right? I just change the signs of everything. So A is equal to mg minus bv squared over m. So as the velocity increases from 0 to something positive, this term here is going to increase, and when you subtract a bigger and bigger number, then the overall fraction is going to decrease. So that tells us that the acceleration decreases. In part C, they ask us to write the differential equation. Well, this is the regular equation, bv squared minus mg equals minus ma. The differential equation only has the variables that we talked about, and it has derivatives in it. So it says that it's okay to have v, t, the given quantities, which are b and g and m. Okay, so our new equation can only have these things in it. So I look at the old equation. B is okay, v is excellent, because that was what we're going to use this to solve. M is good, g is good. Here's m again, and oops, there's a. Can't have a in the equation, so we have to write that in terms of a derivative. The acceleration can be written two ways as a derivative. It's the derivative of the velocity, or we could say that it's the second derivative of the position, which in this case is y, like that. Now, which one of these do we want? Well, we don't have y on our list, so we don't want that. We want the one with v in it, so we're going to stick that in there and write bv squared minus mg equals minus m dv dt. And that's our differential equation. Yay! The last thing, I've run out of room. The last thing we need to do is to find the terminal velocity. And the terminal velocity is when the acceleration becomes 0. So I look back up at this equation here, and I rewrite it again with the acceleration being 0. bv squared minus mg equals 0. And all I have to do, this is now the terminal velocity, v sub t. I just have to solve that. V sub t equals, and I have the answer. Yay!